Welcome to the deep dive. Today, we're plunging into something pretty fundamental to modern AI, stuff you likely use every single day.
Absolutely. Think about, say, the face recognition on your phone,
Yeah, or those translation apps that seem almost like magic,
or even AI mastering really complex games like Go.
right? And what's wild is that a lot of this power comes from a technology that's actually been around since, what, the 1950s? Neural networks.
It's true, a technology with a real history, ups and downs, even what they called an AI winter when funding dried up. But yeah, it's definitely the engine driving things now.
So that's our mission today, a deep dive into these neural networks. We want to get past the hype and really ask, what are they? How do they actually learn anything, being just code?
And that key question, why do we say they learn kind of like the brain, not exactly like the brain?
Yeah, exactly. We'll break down the core ideas, layers, weights, activation functions so you can really get a feel for what's going on under the hood.
And we're drawing insights today mainly from the 100-page machine learning book by Andrei Burkhoff and also Martin Ford's Architects of Intelligence, which has some great interviews.
Okay, let's start there. The name itself, neural network, obviously makes you think of the human brain. That connection is intentional, right?
Oh, absolutely. Artificial neural networks, at their heart, are software trying to roughly mimic how biological neurons connect and interact. And yeah, the idea goes way back.
But it's not a one-to-one copy.
No, not at all. It's crucial to get that. It's more like taking inspiration from the computational principles of the brain at a very abstract level. I mean, let's be honest, we don't fully understand our own brains yet.
Good point. So if it's an abstraction, where does it start? What's the simplest piece?
It starts with something called the perceptron. Think about a real neuron, it has inputs, dendrites,
Right.
a cell body that does some processing, and an output, the axon.
Okay.
A perceptron works in a similar kind of way, but much, much simpler. It takes several numerical inputs.
Numbers coming in.
Yep. And each input gets multiplied by a weight. You can think of that weight as representing the strength of a connection, like in the brain. Some connections are stronger than others.
Okay, so inputs times weights, then what?
Then it just adds all those weighted inputs together. Simple summation.
Just adds them up.
Well, almost. There's one more step. It compares that sum to a threshold value.
A threshold, like a gatekeeper.
Exactly. If the sum reaches or goes over that threshold, the perceptron fires, it outputs a 1. If not, it outputs a 0.
On or off. Binary.
Basically, yeah. And that simple mechanism allows even one perceptron to do a very basic kind of pattern recognition, make a simple decision.
That's clearer, but maybe a concrete example. You mentioned recognizing digits earlier. How would that work for, say, the Norn 8?
Great example. Imagine you have a picture of a handwritten 8-font. You could break that image down into a grid of pixels, maybe 18 by 18 pixels.
Okay, so lots of tiny squares.
Right. That's 324 pixels. Each pixel's brightness, maybe 0 for pure white, 1 for pure black, and shades of gray in between, becomes an input to the perceptron.
So 324 inputs.
Exactly. Each of those 324 inputs gets multiplied by its own specific weight.
So each pixel location has its own importance level.
Precisely. Then all those weighted values get summed up. The perceptron learns, through training, what threshold value for that final sum means, yes, this pattern of pixels looks like an 8.
Okay, I get it for one neuron, but our brains have billions. How do you scale this simple idea up to do complex stuff?
That's the next step. You don't just use one. You connect lots of these perceptrons together. You arrange them in layers.
Layers, okay.
That's how you form a neural network, often called a multi-layer perceptron if it's got, well, multiple layers. This layered structure is really where the power comes from.
So tell me about these layers. What do they do? How does adding layers make it smarter?
Typically, you think of 3 main types of layers. First, the input layer. That's where your raw data comes in, our pixel values for the 8, for example. It's the network's senses.
Got it. Data goes in there.
Then you have the hidden layers. These are the layers in the middle, between input and output. This is where a lot of the computation happens.
Hidden, because you don't directly see the results.
Kind of, yeah. In what's called a fully connected network, every perceptron, or unit, in one layer passes its output to every single unit in the next layer. So information flows forward, getting processed at each step.
Wow, okay. A lot of connections.
It can be, yes. And finally, you have the output layer. This is the last layer, and it gives you the final result or prediction. For something simple like cat or dog, it might just be 1 or 2 units.
Okay, this layering, it makes me think of the term deep learning that pops up everywhere.
Yeah.
Is deep just more layers? Is that all it is?
Pretty much, yeah. That's the core idea. The deep in deep learning isn't some philosophical concept about the AI's understanding. It literally just means the network has many hidden layers, sometimes hundreds.
Huh. So depth equals complexity.
Exactly. Having many layers gives the network much more mathematical flexibility. It allows it to learn patterns within patterns, building up more complex representations of the data layer by layer.
Okay, so we have inputs, weights, layers.
Right.
But you said the perceptron learns the right threshold.
Mm.
And those weights, where do they come from? Does someone program them in?
No, that's the magic. The network learns the right weights itself. This gets us to how these things actually learn. Each unit, each perceptron in every layer has its own set of these internal knobs to turn.
Lobs.
Well, mathematically, they're called parameters. Primarily the weights we talked about, how much importance to give each incoming signal, and usually another one called a bias. Think of it like that unit's baseline tendency to activate.
Okay, weights and biases, those are the things it learns.
Correct. Those are the values the network adjusts during training. But there's another key piece. After doing the weighted sum, each unit applies something called an activation function.
Activation function. What does that do? Is it just the threshold thing again?
It's related, but usually more sophisticated than a simple threshold and absolutely critical. Its main job is to introduce nonlinearity.
Nonlinearity. Okay, math term. Why is that important?
Think about it like this. If everything was just adding and multiplying, even with many layers, the network could only learn very simple, straight-line relationships in the data.
Like drawing a line to separate dots on a graph.
Exactly. But real-world data images, sound, language, it's messy, it's curvy. Nonlinear activation functions allow the network to learn these complex, wiggly boundaries. They let it approximate almost any function, theoretically.
So that's what lets it handle, say, the curve of a cat's ear or the flow of speed.
Precisely. Without nonlinearity, deep learning wouldn't work nearly as well. It's the secret sauce that enables learning complex patterns.
Were there problems with these activation functions early on?
Oh, yes. Some of the older ones, like hyperbolic tangent or sigmoid, had issues, especially in very deep networks. There was this thing called the vanishing gradient problem.
Vanishing gradient. Sounds bad.
It was. Imagine trying to train the network. The adjustments, the learning signal, had to travel backwards through all the layers. With these older functions, that signal got weaker and weaker with each layer it passed through.
So the layers near the beginning hardly learned anything.
Exactly. They learned incredibly slowly, if at all. It made training really deep networks almost impossible for a long time.
So what changed?
A big breakthrough was the introduction of functions like RealU, the rectified linear unit. It's actually very simple mathematically, but it largely solved the vanishing gradient problem. It let the learning signal pass back much more effectively.
Okay, so that enabled much deeper networks.
Definitely. It was a key factor in the deep learning revolution we've seen. Allowed training networks with tens, even hundreds of layers.
Right, so we have the structure. Layers, weights, biases, activation functions. How does it actually learn? How does it figure out the right weights and biases to recognize that cat or when it go?
It learns by practice. Lots and lots of practice, essentially trial and error, guided by data. The most common way is called supervised learning.
Supervised, meaning someone is watching over it.
In a way, yes. You feed the network a huge data set of examples where you already know the right answer. So you give it a picture of a cat, and that picture is labeled cat. Thousands of cat pictures labeled cat. Thousands of dog pictures labeled dog.
Okay, so labeled examples. Then what?
The network looks at an example, say a cat picture. It runs the data through its layers using its current weights and biases and makes a prediction. Maybe it says dog.
Uh-oh. Wrong answer.
Right. So because we know the right answer is cat from the label, we can calculate an error. How far off was the network's prediction?
Okay, it measures the mistake.
Exactly. Then comes the clever part, an algorithm called backpropagation. It takes that error value and works backward through the network.
Backwards.
Yep. Layer by layer, it calculates how much each weight and bias in the network contributed to that error, and then it nudges those weights and biases just a tiny bit in a direction that would have made the error smaller.
So it adjusts its own settings based on the mistake.
Precisely. It makes a tiny adjustment. Then it sees the next example, makes a prediction, calculates the error, backpropagates, adjusts again. Repeat this millions of times over the entire data set, again and again.
Wow, so it's very gradual, iterative learning.
Very gradual, small steps, refining its parameters over countless examples until its predictions become accurate.
Is that the only way these networks learn? Just from labeled examples?
No, that's supervised learning, which is very common. But neural networks are also crucial in reinforcement learning.
Ah, like AlphaGo learning to play Go.
Exactly like that. In reinforcement learning, there aren't explicit labels for every single step. Instead, an AI agent takes actions in an environment like making a move and go,
Right.
and it gets feedback, maybe only occasionally, in the form of rewards or penalties. Win the game, big reward. Lose, penalty. A neural network can be used here to learn which actions are likely to lead to future rewards in different situations. It learns a strategy through trial and error exploration, guided by those rewards.
Fascinating. So it learns the value of actions?
It learns to estimate value, yes, adjusting its weights to make better predictions about future rewards. Very different from supervised learning, but neural networks are the engine there too.
It really does sound incredibly powerful, this whole approach. And I mean, the results speak for themselves, right? Image recognition, translation, AlphaGo.
Absolutely. Deep learning, powered by these neural networks, has genuinely transformed entire fields. It's the main driver behind the AI boom we're living through, no question about it.
But there's always a but, isn't there? It can't be perfect. What are the catches, the limitations?
Oh, definitely catches. It's powerful, but it's just one tool, and it has significant limitations. A huge one is data hunger,
Needing lots of examples.
needing vast amounts of labeled examples for supervised learning. A human child might see one or two cats and get the idea. A deep learning model often needs thousands, maybe millions of labeled cat pictures to get really good.
Wow, that's a big difference. And getting all that labeled data must be hard or expensive.
It absolutely can be. It's a major bottleneck. Another big issue is overfitting.
Overfitting was that.
That's when the network learns the training data too well. It memorizes the specific examples, including noise or irrelevant details, instead of learning the general underlying pattern.
So, like that example you gave earlier, learning that blurry background means animal because all the training photos were like that.
Exactly that kind of thing. It learns a statistical quirk of the data set, not the real concept. So when it sees a new example that doesn't have that quirk, like an animal with a sharp background, it fails.
That really highlights that it's not understanding like we do, is it?
That's a critical point. These networks can be superhuman at narrow tasks, like classifying images or playing Go, but they lack genuine abstraction, common sense, or what's called transfer learning.
Transfer learning.
Yeah, the ability to take knowledge from one task and apply it effectively to a new, different task. Humans are great at this, AI systems. Often they have to be trained almost from scratch for each new problem.
Like the AI that mastered breakout but failed if the paddle moved slightly.
Exactly. It didn't understand paddle, ball, bounce. It learned specific pixel patterns associated with success in the exact training setup. Change the setup slightly, and that learning becomes useless.
So really powerful pattern matchers, but not thinkers in the human sense.
That's a fair way to put it currently. And remember, while inspired by the brain, the artificial neurons are vastly simpler. And the complex architectures we use now, as Martin Ford points out in his interviews, often go way beyond any kind of actual neuroscience inspiration. They're engineered computational systems, not brain replicas.
Okay, so let's try to wrap this up. We've gone through a neural network, starting with the simple perceptron, building up through layers, understanding the importance of weights, biases, and those crucial nonlinear activation functions.
And we saw how they learn, typically through supervised learning with backpropagation, adjusting themselves based on errors over massive data sets,
Right.
or through reinforcement learning with rewards.
Right. It's clearly a powerful data-driven technique that's, well, changed everything in AI.
And the relevance for everyone listening is huge. This stuff isn't science fiction anymore. It's in your phone, your web searches, your smart assistants.
Yeah, understanding the basics really helps you appreciate what AI can do now, but also, maybe more importantly, what its current limits are. It's not magic.
Exactly. Knowing about data hunger, overfitting, the lack of real understanding, it grounds the hype.
So here's a final thought to leave everyone with. If these powerful neural networks are inspired by the brain, but still so different, needing tons of data, struggling with common sense, what does that tell us about intelligence itself?
Does true, flexible, human-like learning require something fundamentally different, something beyond just finding patterns in data, something closer to actually understanding the why behind it all?
Something to definitely ponder. That's all for this deep dive. Thanks for joining us.